Hello everyone, welcome to the series of lecture on actinide chemistry, and today we are going to discuss about the active chemistry of block elements, that is lanthanides and actinides. Prior to the lecture, I just assume that most of you have gone through the earlier lectures of actinide chemistry, in which the basic ideas of actinide concept, their position into the periodic table, and their electronic configuration is already discussed. So I will not go into the details of those concepts. So first of all, I just want to add that these books that I have used for my references and some of the sources that I have taken from the internet. So I've used primarily this book, that is the Chemistry of Actinides and Transactinide Elements, for my reference, in which I have generally considered chapters, that is chapter 15 and chapter 23. I've used Medusa or Hydra based software for the speciation plots. I've also taken some information from internet and web for this presentation. So as you already know about the electronic configuration of lanthanides and actinides, but just to brief you, or just to start the presentation, I've shown you the electronic configuration of actinides and electronic configuration of lanthanides. If you see, I've also given you the electronic configuration of the trivalent lanthanides and actinides. If you see the lanthanides and actinides, what you find common between the two, that in actinides, when you talk about the trivalent state, the f electron filling goes from F1 to F14. And very similar case arises when you talk about the electronic configuration of lanthanide from 4F1 to 4F14. So when you see the tri-positive starting from F1 to F14 filling is there, but when you talk about the atoms rather than this tri-positive state, you find certain differences. Suppose this one. So why this kind of differences arises? Most of these things has been already discussed, so I will not go into the detail. But one thing I just want to convey you that if you see this, there the occupancy of d orbitals are there. What they suggest that the f and d orbitals are close to each other. But after that, if you see the electronic configuration prefer f and 7s2 kind of system. So you can see generally that to talk about the actinide, then 5f and 6d1 and 7s2. This kind of electronic configuration is preferred when n is equal to 2 to 4. But when you go beyond n is equal to 6, what is there? The configuration that is most preferred is FNN 6D0, there is no electron, and 7s2. So this preference goes up to americium, and after that you can again see the involvement of d orbital. That basically comes from the half-filled shell, that is F7 and 4F7 and 5F7. So with this basic understanding of electronic configuration, we would like to see some of the differences and similarities into the lanthanides and actinides. As we all know that when we talk about the actinides and lanthanide, the actinides start from actinium and ends at lawrencium, whereas talk about the lanthanides, they start from lanthanum and ends at lutetium. The filling of f electron starts at cerium in the case of lanthanide, whereas the filling of f electron starts at protactinium in the case of actinides. Most of the lanthanides are naturally occurring except promethium, which is a fission product, whereas actinides are generally man-made, and only few of them, such as actinium, thorium, protactinium, and uranium, the first few in the series, can be found in the nature. So when you talk about the similarities, as we have seen in the electronic configuration, both lanthanides and actinides use f orbital as a part of active valence orbital. Both lanthanides and actinides, when you go from left hand side to the right hand side, when you move like this, there is decrease in the size. So that is basically due to contraction. So we say this as a lanthanide contraction in the case of lanthanide and actinide contraction in the case of actinides. We'll try to discuss this again in the upcoming slides. When you see the tri-positive metal ion, if you see these two, they have F7 configuration, both gadolinium and curium. and the trivalent state, whether this or this, they behave in very much similar way when you talk about the trivalent state in both lanthanide and actinide. But what the difference is? There are several differences that mainly arises because the lanthanides use 4F whereas actinides use 5F. The mainly differences arises because they are using different kind of shell. The first difference you can say is that 6d orbitals are energetically accessible. And what does it mean? That, as I've shown you in the previous slides, that if you start filling of electron in the early elements of actinide versus lanthanide, you can see there is no d orbital, whereas there is d orbital. What it suggests that the F and D are close, they are energetically very close. So in actinides, these three orbitals, that is 5F, 6D, and 7S, they are energetically very close. That I have written in the next line, that 5F orbital of actinides are in close energetic proximity to the 6D and 7S orbitals, whereas if you talk about the 4F electrons, they are shielded more effectively than the 5F electron. That you can see from this graph also. This is the 4F, this is the 5F. So if you see the 5F is more diffused compared to the 4F. And if you see the energy difference between 4F and 5D, and if you see the 5F and 6D, if you see 5F is here, 6D is here. So they have quite a good amount of overlap. But when you see the other one, that is the 4F and the corresponding 5D, the overlap is very, very small. So this makes their energy very close to each other. Similarly, when we talk about the valency of these actinides, because these three are very close to each other, so you can remove electron either from S or D or F. So because of this, they show variable oxidation state into the aqueous media. So let us see something about this oxidation state. So when you talk about these lanthanides, they have group oxidation state of 3. What does it mean? That most of the lanthanides are having only oxidation state of 3. But if you see the actinides, you can start from 3, 4, 5, 6, 7, and sometimes 2 also. So you can see when you talk about the actinide, the oxidation states vary from +2 to +7. Whereas when you talk about the lanthanides, it's mainly +3. Why is it like so? Even one more peculiarity about the actinides is the existence of multiple oxidation states at a single time. For example, plutonium. You can see most of the oxidation state in the case of plutonium exist at the same time into the solution. How it is possible? To understand that, let us see the redox potential of these actinides into the solution phase. So here I have given you the redox potential of uranium, neptunium, plutonium, and the corresponding couples such as uranium-6 to uranium-5, uranium-5 to uranium-4, and to uranium-4 to uranium-3. And this all is in 1 molar perchloric acid. So if you see very carefully, the first couple is having a reduction potential of 0.06. Next couple is almost 10 times higher. And the next one is again going to the negative direction. So there is a huge difference from uranium-6 to uranium-3 couples. When you see the neptunium case, again you can see the neptunium-6 is plus 1.136, whereas neptunium-5 to 4 is 0.739, and again it is getting reduced to 0.155 in the case of neptunium-4 to neptunium-3. So again you can see there is a difference. What about the plutonium? The first one is from plutonium-6 to plutonium-5 is 0.916. Second one is hardly 0.25 units ahead, that is 1.17. Third one is very close, again 0.98. So even this one, if we are directly going from plutonium-6 to plutonium-4, again it is in the range of 1.043. What it means that most of these redox potentials are very close to each other. What does it suggest? That most of these species can coexist at a given solution condition. So actinides show this kind of very peculiar behavior, that sometimes the coexisting oxidation states are also possible for a given element. We'll now see that how the individual oxidation states are varying. As I've shown you that the actinide can have +2 to +7. What are the elements that exist in +2? And obviously +3, +4 to +7. So first off, we'll talk about the divalent ion. The only possible or only actinide that prefer this state is novalium. You can see here. And along with this, I have given you the electronic configuration in the M3 plus state. So it is the M3 state that is giving me F30. Suppose I go to M2 plus, it will be F30. So the extra stability of this is coming because of the F14 configuration, that is a closed shell configuration. But the same is not true if you see the corresponding lanthanide. In lanthanide, if you see ytterbium, it doesn't prefer plus 2. It is not preferring plus 2. It is preferring plus 3. That can be explained just by looking at the electrode potential. If you see the plus 3 to plus 2, that the redox potential, if you see, it is highly positive, plus 1.45. So the energetically this transformation is very much favorable. So the tendency of novalium going to 2 from 3 is very much favorable. But if you see the ytterbium 3 to 2, it is negative. And the corresponding delta G for this should be positive. So this kind of transformation is very difficult. So that explains that why ytterbium 2 is not stable. Although one can see that both of these, when you talk about the novalium and ytterbium, they have electronic configuration that is F14 when they are in the divalent state. So what it means that rather than the stability of F14, that is the closed shell configuration, there could be other factors that decide the stability of the metal ion into the aqueous phase, that may be related to the relativistic effect that is very much different on the 4s orbital and the 5s orbital, or due to the interaction of these orbitals into the aquatic media, because of which the oxygen states differ from 2 to 3. When we talk about the trivalent ion, starting from americium to mendelevium, everything can be present in the trivalent. So you can say americium to mendelevium along with lawrecium, they can be trivalent. But if you talk about the lower part, that is plutonium, neptunium, uranium, protactinium, or thorium, there is very much difficulty in preparing the trivalent state. In plutonium, you can prepare trivalent using some reducing agent, but the moment you prepare, they tend to get oxidized to plutonium 4. Most of the time, this happens because of the reduces of the water that will be there, because when we see a plutonium solution, we know that it will give some alpha particle, and this alpha particle has tendency to do some radiolysis, and because of that radiolysis we produce several ions and several radicals that are very reactive. They can be oxidizing, they can be reducing. So it so happens that when you have a solution of plutonium 3 which is giving you continuously some alpha particle that lead to radiolysis of the water and producing this kind of very reactive species, the plutonium 3 get oxidized to plutonium 4 because of the radiolysis. To confirm that, what people have done that they have used the plutonium that having a very large half-life, such as plutonium 242 or 244, and but they have seen that when you are using this plutonium where the half-life is quite large, it means the alpha emission is low, then their stability in the plus 3 is quite large as compared to the plutonium isotope where the alpha emission is very frequent, or you can say its half-life is very small. When you talk about the neptunium and uranium, again they are very difficult to stabilize, and most of the time they require inert atmosphere for the stability. Thorium and protactinium, they are almost very difficult to form, and they are not even stable in the solution phase. Let's talk about some tetravalent ion. So when you talk about the tetravalent, starting from thorium to californium, everything can be prepared in the tetravalent form. But if you talk about the stability, the most stable one is thorium and plutonium. The others are such as protactinium, uranium, and neptunium. They can be made stable, but you require absence of oxygen. But plutonium 4 is obviously stable, and even in the presence of oxygen, it is quite stable. The other actinide that is stable is berkelium. You can see from here. That is stable because of the F7 configuration of +4 states. So that is extra stability comes because of the F7 configuration in the case of berkelium. And as I've shown you in the earlier slide, all the plutonium is stable in +4, but that is not the only oxygen state that is there in the plutonium solution. All the oxygen states starting from +3 to +6 can coexist in the case of plutonium. When I talk about the other elements such as americium, curium, and californium, they are very difficult to prepare in the +4. And even if you try to prepare them using some reducing condition, you need strong complexing agents such as chloride or phosphate to get stabilized into the +4 state. Let us see about the pentavalent ion. Again, you can see that from protactinium to americium, they can be made into the pentavalent state, but the stable pentavalent is protactinium and neptunium. Rest all are very much unstable, and the most of the time this instability comes from the disproportionation. What is disproportionation? That I will just discuss in the next slide. So they are unstable with respect to the disproportionation. When I talk about the hexavalent ion, again, from uranium to americium, they all can be prepared in the hexavalent state, and the most stable one is the uranium. That if you see uranium is stable, that is because of the F0 system. If you see uranium 6 doesn't have any electron in the f orbital. And if you talk about the relative stability, again, uranium 6 is very much stable compared to plutonium 6, which is stable compared to neptunium 6. And that can directly be seen from the corresponding redox potential. If you see, the reduction from 6 to 5 is not very much feasible. It is only 0.063. So delta G is not very feasible. But we talk about from neptunium 6 to neptunium 5, this is very much feasible. So that explains the trend that why neptunium 5 is so stable and uranium 6 is so stable. When we talk about the heptavalent state or the +7 states, possibility is neptunium and plutonium. That too in the alkaline medium. In acidic medium, they do not exist as a heptavalent ion. So with this information of different kind of oxidation state into the aquatic media, let us try to see that, because as we know that the stable states are from +2 to +7 in the actinide under different set of conditions. Some of them have a different structure altogether. Let us see how they differ. So as I showed you that for actinides you can have starting from +2 to +7, but ions in +2, +3, +4, they are spherical. But what about +5 and +6? So when you see this +5 and +6, they are not existing as a spherical ion, because here the ionic potential of +5 and +6 is so high that they extract the oxygen from the media and they make this kind of linear compound, which are known as linear dioxocations. So you can see here for the pentavalent, this actinide is obviously having pentavalent state. So you can say pentavalent -2 here, and oxygen -2 is total charge is plus. If you see the hexavalent, obviously +6 -2 -2, so charge is 2. So they exist as a linear dioxocation, but not all pentavalent. This is mainly true for neptunium onward. What about the pentavalent state of titanium? This does not exist as this. The most stable form of this is monooxy with either 1 or 2 hydroxyl group, and depending on the number of hydroxyl group, the oxygen state of the totalis can be +2 to +1. So this difference that exists, that although this is the most stable state of protactinium, just like neptunium, but this doesn't exist as diazocation, because the formation of the diazocation is very very difficult because of the some symmetry of orbitals, and they cannot make these pi bondings with the oxygen, the second oxygen basically, and they prefer to remain in this form. When I talk about the heptavalent, obviously, as I told you that they are only stable in the alkaline media, and the form in which they are stable is actinide O4 OH 3-. So we know that yes, these are the states and these are the basic forms. You can say that the stability of these forms in the aqueous phase, and some of them are existing as a spherical, and some of them are existing as a linear ion. We say that is a linear ion, like this. You have actinide and the corresponding either plus or 2 plus, depending whether they are pentavalent or hexavalent. So let us see. As I told you that most of the time the pentavalent states are very much unstable because of the term called disproportionation. What is disproportionation? Disproportion is nothing but you start with one oxygen state, let us say 5, and that will result into two oxygen states, that is plus 6 and it is the splitting of one oxygen state into one higher and one lower oxygen state. That is very much common for the pentavalent ion. As you can see, uranium, neptunium, or plutonium, all of them undergo disproportionation. And if you see the equilibrium constant, that is very, very high for the uranium compared to neptunium. That again suggests that neptunium 5 is more stable compared to uranium 5. And when they disproportionate, what they are forming is a lower oxygen state, that is uranium 4, uranium 6. Similarly, when you talk about the neptunium, then you talk about the neptunium, that is NPO2 plus. It will take up 4 proton, form NPO plus, NPO2 plus, plus 2H2. So neptunium again starting from 5, going to 4, and to 6. So this is disproportion that is mainly happening for the pentavalent, but there are other ions also, such as this. You can see the two oxygen states are combining to give two new oxygen states. So this is very common in the actinides, that disproportion reactions that is there for the actinide. So now with the knowledge of the exact spherical or linear ion in the actinide and their oxygen states, let us talk about how the sizes of these ions are varying. As I told you that when you talk about plus 2 to plus 4, they are mainly spherical. And when you talk about plus 5, plus 6, they are mainly a linear ion. So here we have seen the ionic radii of the actinides as well as lanthanide ion in plus 3 and plus 4. I have not shown for plus 5 because they are not spherical. They are basically linear compound. If we see that there is a steady decrease, whether we talk about the lanthanide or we talk about the actinide, there is a steady decrease in the ionic radii of this with the atomic number. Why? Because when we talk about the lanthanides, this 4f, or in the case of actinide, this orbital, they contribute to a very poor shielding, and because of the poor shielding, whatever electrons we are adding when we are going from here to here, they are feeling more effective charge, and because of this there is a contraction, and this is linearly decreasing. And why the size is different from lanthanide to actinide? Obviously we are going from 4f here to 5f, so the size is on the higher side. Again, in the tetravalent also you can see there is a steady decrease in the size because of the contraction. So this is basically lanthanide or actinide contraction that basically happens because of the poor shielding of valence electron by f orbital. One more very interesting effect that is very important when you talk about the heavier atoms is called relativistic effect. What the effect is, when you are in the zone of this high atomic number, such as actinium, sodium, or protactinium, such as very high atomic number, what will happen that we have a nucleus, right? And the electrons are revolving around them. So when you are increasing this atomic number, the electron feel more and more pull from the nucleus, and its speed keeps on increasing. When you go to a very high atomic number, such as in the lanthanide or actinide, this attraction is so much that the speed goes close to the speed of light. And when the speed goes to the close to speed of light, there is something that is called the relativistic mass that is different from the rest mass. And if you compare them, when your V is going close to C, your relativistic mass of the electron keeps on increasing, and your relativistic mass and your Bohr radius are inversely proportional. When the mass is increasing, the Bohr radius, when the mass is increasing, the Bohr radius is contracting. And this effect is very much prominent for S and P orbitals. So you can say that S and P orbital will try to contract, but when we talk about the other two, that is D and F, they feel opposite effect. Why? Because since S is getting contracted and P is getting contracted, now the shielding of nucleus, or the shielding of nuclear charge for the outer electrons are very high. So they contract and they shield the outer orbital. And because of that, D and F do not feel that much amount of attraction from the nucleus. And instead of getting contracted, they expand. So this is something called direct relativistic effect. And this is something we say like indirect relativistic effect. The same thing you can see in the figure that happened. That's shown here. When you talk about the S and P, if you see, if I am considering the relativistic domain and non-relativistic domain, in the non-relativistic domain, the orbital is here. But the moment we apply this relativistic corrections, the orbital shifted. Same you can see the p orbital. This is non-relativistic and this is relativistic. So you can say there is a shift towards the nucleus. But what about the F and D? The non-relativistic is this side, where the relativistic is shifted towards right. So there is a destabilization of, you can say, destabilization of D and F, where there is a stabilization of S and P. So because of this relativistic effect, also the contraction of the lanthanides and actinides occur, and almost 10 to 15% of the lanthanide or actinide contraction can be attributed to this relativistic effect. So when we talk about this linear ions, there obviously I will not talk about this contraction and sizes, because the linear ion, that is penta and hexavalent, they are basically existing as a linear ion. So this is for hexavalent, and similarly I can write for pentavalent also. And there the concept of this reduction in the ionic radiation we are not going to discuss, because they are linear, they are not spherical, and this concept is mainly we are discussing for the spherical ion. So the first thing that can happen when you have a metal ion, you know about this size, you know about the radius, and you put them into the water. What will happen? They will try to hydrate themselves. What can happen? You have a metal ion, you put into water, there can be a primary hydration layer just on the metal ion. That is, we have given NH2O, and it can be a total hydration, which includes both primary and the secondary, that I have given the name H. That is obviously primary plus secondary. So the moment you put, there are hydrogen structures around this metal ion. So let's talk about the trivalent metal ions and what are the hydrogen structure around the trivalent metal ion. We can determine this hydrogen structure obviously, because we need to know that how many are there in the primary sphere, and we want to know that how many is there in the secondary sphere. Or if we can get information about the total, we can get secondary just by subtracting the primary one from the total. So there are two techniques generally people use to get information about the primary hydrogen sphere, that is fluorescence and exhaust. Whereas to get information about the total, you are mainly relying on the electrophoretic mobility kind of experiments, in which we measure some kind of diffusion which will tell about the overall radius of the structure. And since we know about the radius of this, we'll try to deduce that what is the total hydration, and from this total hydration we subtract primary hydration that we can directly get from these techniques, and we can get the value of the secondary hydration number. So now how these hydration numbers are changing for the trivalent metal ion. So if you see the trivalent metal ion and you start from this end, this is shown here, the initial hydration level shows almost 9 water molecules. But the moment you go from left to right, what you see, there is a decrease, and start from 9 and get settled down 8. Why there is a change from 9 to 8? When we are at this position, obviously as shown in the previous slide, So since the sizes are large, they can accommodate. Since the size is a bit larger, you can accommodate almost 9. But the moment you move like this, your size keeps on reducing. So now because of the steric factor, accommodating 9 water molecules are very difficult. So they settle down with 8. And the very similar case happens with the actinides also. And this transition, when you see this particular area, that happens for lanthanides at promethium and dysprosium, whereas for actinides it happens at americium to einsteinium. Why this smooth transition? Because at this particular place, whatever metals are coming, such as suppose americium here, they can have both. Some of them can have 9s2, some of them can have 8s2. So the hydrogen sphere can have 9 or 8. So they have this kind of mixture, and because of that, they fall on this line. What about the secondary hydration? If you see the secondary hydration, this is just reverse. Although the primary is decreasing from 9 to 8, the secondary, when you are going from cerium to terbium, this keeps on increasing. Why so? Because as we are reducing the size, but we are not reducing the charge, everyone is trivalent. So the Z by R ratio, or you can say the ionic potential, is keeps on increasing. And although because of their particular size, they cannot accommodate more water into the primary sphere, but because of their electrostatic field that can extend, they can now accommodate more water molecule into the secondary sphere, if sort of the secondary sphere. And the total is obviously on the larger size. So here comes the role of ionic potential, that is the surface ionic potential. And this happens because of the, again, when you talk about the tetravalents, in tetravalent, such as thorium, we are having generally 10 to 11 water molecules. What about pentavalent? The case of pentavalent, again, as I've told you, that it's a little special when you talk about pentavalent and hexavalent, because pentavalent do exist as a linear cation that I've shown here. And the two positions that we say the axial are already occupied or already blocked by the oxygen, and you are only left in the equatorial plane. So when we talk about this, then the chances of water coming into the plane of this Neptunium is restricted in the equatorial plane only. And generally, 5 to 6 water molecules are present in the actinide. When you talk about the pentavalent actinide or hexavalent actinide, one very interesting aspect that is very much peculiar to the actinides, or basically to the pentavalent ions, are cation-cation interaction. When the concentration of these actinides are very low, then obviously they exist as a hydrogen ion. But suppose you have a medium in which you are having both Neptunium 5 and uranium 3. Suppose you are having both. So uranium 6, obviously that is U22 plus, Neptunium, that is NPU2 plus. Both are a linear cations. So when they are present together, the chances are there that the cations can interact with each other. And the mode in which they interact, one is called T-shape and one is called diamond. And this kind of shapes are very, very common in the solution. Why the interaction is taking place? Why such an interaction is there? To understand that, you can think of the concept of residual charges. What is the residual charges? Although I have shown you that the pentavalent actinide that we write as AnO2 plus, we say they are pentavalent, but since they have oxygens here, and oxygens donate part of their electron density to these actinides, it so happens that if you see the charges on the actinide, they are not exactly penta or hexavalent, they are not exactly 5 or 6. What happens that if you talk about neptunium, let us say NpO2 plus, and if you see the charge on neptunium exactly, it will be around 0.2, 0.2. Whereas if you see about the uranium, that is U2 2 plus, and you try to see the charge on uranium, then it is around plus 3.3. So these charges are different than whatever we see, that whether they are pentavalent or hexavalent, but which is the actual charges, it is basically 2.24 pentavalent and 3.34 hexavalent ion. And now, since the charges are different, this again has some partial negative charge. And this partial negative charge can interact with the positive charge of uranium, which is 3.3. And they can make this kind of complex, which is known as cation-cation complex. And it is very, very unique properties of the actinide, that cation-cation formation, with, not with uranium only. You can have other metal ion also. For example, you can have thorium also. And as the charge is increasing, the interaction is getting stronger and stronger. So with this, I want to end this particular lecture, and we'll discuss about the other concept in the next coming lectures. Thank you very much.